Hi everyone, welcome back to part 2 of the AP Calculus AB 2014 FRQ. Today we'll be looking at questions 5 and 6. Question 5 gives us a chart and says the twice differentiable functions f and g are defined for all real numbers x. Values f, f prime, g, and g prime for various values of x are given in the table above. Part A asks us to find the x-coordinate of each relative minimum of f on the interval -2 to 3 inclusive and to justify our answer. Relative extrema of a function, f of x, takes place at its critical points when f prime of x, the first derivative, is equal to 0. Additionally, we know that the first derivative test states that at that critical point, f prime of x has to change signs for it to be an actual extrema. So taking a look at the f prime of x row in the chart, we see that on the interval -2 to -1, f prime of x is negative, and from -1 to 1, it's also negative. So even though there is a critical point at -1, the sign of f prime of x does not change, so this is not a relative minimum. At x is equal to 1, there is a second critical point. This time, f prime of x does change signs from negative to positive. We know by the first derivative test that if f prime of x goes from negative to positive on a certain critical point, then that critical point is a relative minimum. So your answer for part A would just be x is equal to 1, because f prime of x is equal to 0 and changes signs. Part B says explain why there must be a value c for the open interval -1 to 1 such that f double prime of c is equal to 0. Now, unlike the previous part where we used the intermediate value theorem to state that there must be a certain value that f of x takes, we cannot use the intermediate value theorem here because we're looking for the derivative. We're trying to explain why the derivative must take on a certain value, not f of x itself. So instead, let's use the mean value theorem. The mean value theorem states that given a function that is both differentiable and continuous, it will be guaranteed that the slope of the secant line going through its endpoints will be equal to the slope of the tangent line at some point along that graph. So if we're looking for a value that is between -1 and 1, then we know that the interval we're dealing with is -1 to 1 inclusive, because these would be our endpoints, and then our c would be between these endpoints. Now we know that on this interval, f prime of x, if f prime of x is continuous, and differentiable. So now let's find the slope of our secant line from our endpoints, -1 and 1. So f prime of 1 would be 0, and then f prime of -1 is also 0. So 0 over anything, in this case it'd be 1 minus -1, which equals 0 over 2, is just equal to 0. So we know that this is the slope of the secant line. Slope of secant. And according to the mean value theorem, MVT, this slope of the secant line is also equal to the slope of the tangent line. So slope of tangent. So because of the mean value theorem, we know that at some point the slope of the secant line, 0, will equal the slope of the tangent line. And the slope of the tangent line of f prime is just f double prime. So we know that there must be a value c on this interval such that f double prime of c is equal to 0. Part C reads, the function h is defined by h of x equals the natural logarithm of f of x, and it asks us to find h prime of 3. So we know that the derivative of a natural logarithm, it's 1 over the quantity. So h prime of x is equal to 1 over f of x. But now the chain rule kicks in. The chain rule states that after we take the derivative of the outside function, we have to go inside the compound function. So the derivative of f of x is f prime of x. Now we evaluate both sides at x equals 3. So this becomes h prime of 3 is equal to 1 over f of 3 times f prime of 3. Looking back at our table, we can see that f of 3 is 7, and f prime of 3 is 1/2. So this becomes 1 over 7 times 1/2, which is equal to 1 over 14. Part D asks us to evaluate the definite integral from -2 to 3 of f prime of g of x times g prime of x dx. So if we look at our integrand inside the integral sign here, we'll notice that this is the composition of a chain rule, basically. So if you notice, someone took the derivative of the outside function, f prime of g of x, and then went inside and took the derivative of g of x. So this is g prime of x. So we can figure out that the function that was integrated was f of g of x. We also know that the fundamental theorem of calculus says that in order to evaluate this definite integral, what we do is find the original function of the integrand, that is the function that was that we took the integral of, and then we plug in 3, and then we subtract it from that original function, evaluated at -2. So let's write that down here for part D. So the definite integral from 3 to -2 of f prime of g of x times g prime of x dx is equal to the original function that we integrated. In this case, that would be f of g of x, evaluated at the top bound, 3, and then minus this function evaluated at the bottom bound, -2. So we can rewrite this as f of g of 3 minus f of g of -2. G of 3 is 1, and g of -2 is -1. So this becomes f of 1 minus f of -1. F of 1 is 2, and f of -1 is 8. So this is 2 minus 8, which equals -6. Now moving on to the last question, question 6. Question 6 tells us to consider the differential equation dy over dx is equal to the quantity 3 minus y times cosine x. That y equals f of x be the particular solution to the differential equation with the initial condition that f of 0 is equal to 1. The function f is defined for all real numbers. Part A says, a portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. So remember that these slope fields illustrate the slope of the graph at each particular point. So the point 0, 1 is right here, and our solution curve that passes through this point seems to follow this general pattern right here. Part B asks us to write an equation for the line tangent to the solution curve in part A at the point 0, 1. Use the equation to approximate f of 0.2. So the slope of the line tangent to the solution curve at a certain point is equal to the derivative of the solution curve at that certain point. And luckily for us, the AP provides us the differential equation that models the value of the first derivative with respect to x and y. So we know that the slope, wrong color, sorry. We know that the slope of the tangent line is just equal to dy dx, which is equal to 3 minus y times cosine x. Now we know that this line that we're looking at is tangent to the curve at the point 0, 1. So let's evaluate this at the point 0, 1. So 3 minus 1 is just 2 times cosine of 0 is equal to 1. So 2 times 1 is 2. So m is equal to 2. So now we can use point slope form. Y minus 1 is equal to 2 times x minus 0. So y is equal to 2x plus 1. And this is the equation of the line tangent to the solution curve. So in order to use this equation to estimate f of 0.2, all we need to do is plug in 0.2 for x. So this becomes y equals 2 times 0.2 plus 1, which equals 0.4 plus 1. So our estimate is 1.4 is f of 0.2. Part C reads, find y is equal to f of x, the particular solution to the differential equation with the initial condition f of 0 is equal to 1. So the only method of solving differential equations we are responsible for on the AP exam for 2020 is separation of variables. So let's do that here. So for part C, dy dx is equal to the quantity 3 minus y times cosine x. When we separate these variables, we want to get the dx and the dy on the same side as their respective variables. So let's move the 3 minus y to this side, and then move the dx to this side. So this becomes dy over 3 minus y is equal to cosine x dx. Now we can take the integral of both sides to get rid of the dy dx and be left with a y equals f of x form equation. So the integral of this side would just be the natural logarithm of 3 minus y times negative 1 because of the reverse chain rule here equals the antiderivative of a cosine is just sine, so this is sine x, plus our constant of integration c. And just on a little bit of a tangent, there's technically a constant of integration on both sides because we're taking two integrals. I know I've mentioned this before, but I'll do it again. What basically ends up happening is when you simplify this equation and you subtract this constant of integration from both sides, you're still left with a constant, because even if you subtract this one from this one, you're left with another constant of integration. So really, we only need one, which is why you don't see me writing two constants of integration. So let me get rid of all this. Now we can solve for our only constant of integration with the initial condition that f of 0 is equal to 1. So if we plug in 1 for y and 0 for x, we get negative natural log of 3 minus 1 is equal to sine of 0 plus our constant. Sine of 0 is 0, so we get our constant is equal to negative natural logarithm of absolute value 2. So now we can write our solution as the natural logarithm of 3 minus y times negative 1 equals sine x minus the natural logarithm of absolute value of 2. We can further rearrange this as the natural logarithm of the absolute value of 3 minus y equals negative sine x plus the natural logarithm of absolute value of 2. Now, to get rid of the natural logarithm on the side of the y, we can apply the number e to both sides. So we take e raised to the natural logarithm of the absolute value of 3 minus y, and this set it equal to e raised to the power negative sine of x plus the natural logarithm of absolute value 2. E raised to the natural logarithm of anything is just that anything, so this is 3 minus y, the absolute value. And we know from our exponent rules that we can break this term up into e to the negative sine x times e to the natural logarithm of absolute value 2. And just like with the left side, we know that e raised to the natural logarithm of anything is just that anything. So this becomes absolute value of 2, which is just 2 times what we had before, e raised to the negative sine x equals. And if we take a look at this absolute value expression that we have here, we know that we don't want to deal with absolute value, because remember, when you solve for an absolute value equation, more than likely you're going to get two answers. You're going to get a negative answer and then a positive answer. But luckily for us, if we look up here at our original solution curve that we drew using the slope field, we can get the basic idea that your y value will always be less than 3. So if your y value is always less than 3, that means that this expression here is always going to be positive. So we can just rewrite this absolute value term here into just normal 3 minus y. Now we just need to move 3 to the other side, so this becomes this expression minus 3, and to multiply everything by negative 1 to get y is equal to 3 minus 2 times e to the negative sine x power.